everyone and welcome back! Today we're going to prove a beautiful and challenging formula from calculus, the Maclaurin series explanation of tangent function. At first glance, the coefficients in this series may look mysterious. Where do numbers such as 1/3, 2/15, 17 over 315 and 62 over 2835 come from? And how can we systematically derive all of them? That is exactly what we're going to discover today. So stay with us until the very end, because we are going to derive this formula step by step rather than simply memorizing it. In this proof, you will see where every coefficient comes from and how the general recurrence relation is constructed. Let's begin. State the problem. Our goal is to prove Maclaurin series expansion of tangent function. Tangent of x equals x plus x cubed over 3 plus 2x to the 5th over 15 plus 17x to the 17 over 315 plus 62x to the 9th over 2835 plus 1382 x to the 11th over 155,925 plus 21,844 x to the 13th over 6,081,075. But where does this complicated sequence of coefficients come from? Let's derive it from first principles. Introduce the tangent function. Let us define y equals tangent of x. The derivative of tangent x is secant squared x. Therefore, y prime equals secant squared x. We also know the fundamental trigonometric identity. Secant squared x equals 1 plus tangent squared x. Since y equals tangent of x, we can write y prime equals 1 plus y squared. Also, y of 0 equals 0. Because tangent of 0 equals 0. So instead of directly calculating many complicated derivatives of tangent, we'll use the much simpler differential equation. Y prime equals 1 plus y squared. Assume a Maclaurin series. Now assume that y can be represented by a Maclaurin series. Because tangent is an odd function, tangent of negative x equals negative tangent of x. Only odd powers of x can appear. Therefore, we write y equals a sub 1x plus a sub 3x cubed plus a sub 5x to the 5th plus a sub 7x to the 7th plus a sub 9x to the 9th. Differentiate the series. Now differentiate this series term by term. Y prime equals 1 plus 3a sub 3x squared plus 5a sub 5x to the 4th plus 7a sub 7x to the 6th plus 9a sub 9x to the 8th plus 11a sub 11x to the 10th plus 13a sub 13x to the 12th. Our differential equation is y prime equals 1 plus y squared. Therefore, we need to calculate y squared. Starting with y equals x plus a sub 3x cubed plus a sub 5x to the 5th plus a sub 7x to the 7th, and so on. We square both sides. Y squared equals x squared plus 2a sub 3x to the 4th plus the quantity 2a sub 5 plus a sub 3 squared times x to the 6th plus the quantity 2a sub 7 plus 2a sub 3a sub 5 times x to the 8th plus the quantity 2a sub 9 plus 2a sub 3a sub 7 plus a sub 5 squared times x to the 10th, and so on. First, compare the coefficients of x squared. From y prime, the coefficient of x squared is 3a sub 3. From 1 plus y squared, the coefficient of x squared is 1. Therefore, 3a sub 3 equals 1. And hence, a sub 3 equals 1/3. Now compare the coefficients of x to the fourth. 5a sub 5 equals 2a sub 3. Substitute a sub 3 equals 1/3. Then 5a sub 5 equals 2 times 1/3, which equals 2/3. Therefore, a sub 5 equals 2/15. Now compare the coefficients of x to the sixth. 7a sub 7 equals 2a sub 5 plus a sub 3 squared. Substitute a sub 5 equals 2/15 and a sub 3 equals 1/3. Then 7a sub 7 equals 2 times 2/15 plus 1/3 squared. So 7a sub 7 equals 4/15 plus 1/9. Using a common denominator, 7a sub 7 equals 12/45 plus 5/45, which equals 17/45. Therefore, a sub 7 equals 17 over 315. Now compare the coefficients of x to the eighths. 9a sub 9 equals 2a sub 7 plus 2a sub 3a sub 5. Substitute the known coefficients. 9a sub 9 equals 2 times 17 over 315 plus 2 times 1/3 times 2/15. Therefore, 9a sub 9 equals 34 over 315 plus 4 over 45. Since 4 over 45 equals 28 over 315, we get 9a sub 9 equals 62 over 315. Therefore, a sub 9 equals 62 over 2,835. The sum from k equals 0 to n minus 1 of a sub 2k plus 1 times a sub 2 n minus 2k minus 1. Derive the general recurrence relation. Now we can see the general pattern. The coefficient of x to the 2n in y prime is 2n plus 1 times a sub 2n plus 1. The coefficient of x to the 2n and y squared is the sum from k equals 0 to n minus 1 of a sub 2k plus 1 times a sub 2n minus 2k minus 1. Because y prime equals 1 plus y squared, these two coefficients must be equal. Therefore, we obtain the recurrence relation. 2n plus 1 times a sub 2n plus 1 equals the sum from k equals 0 to n minus 1 of a sub 2k plus 1 times a sub 2n minus 2k minus 1. This recurrent relation is the key to generating all the coefficients of the Maclaurin series. Put everything together. We have now calculated the coefficients one by one. They are a sub 1 equals 1, a sub 3 equals 1/3, a sub 5 equals 2/15, a sub 7 equals 17 over 315, a sub 9 equals 62 over 2,835, a sub 11 equals 1,382 over 155,925, a sub 13 equals 21,844 over 6,081,075. Substituting these coefficients into our original series gives tangent of x equals x plus x cubed over 3 plus 2x to the 5th over 15 plus 17x to the 7th over 315 plus 62x to the 9th over 2835 plus 1382x to the 11th over 155,925 plus 21,844x to the 13th over 6,081,075. Radius of convergence. Finally, we should state where this Maclaurin series converges. The tangent function has its nearest singularity at x equals positive p over 2 and x equals negative p over 2. Therefore, the radius of convergence is r equals p over 2, and the series converges for x is greater than negative p over 2 and less than positive p over 2. I hope you enjoyed this challenging proof and found the method useful. If you enjoyed this problem, stay tuned for more challenging mathematical proofs and advanced formulas. We will be exploring many more beautiful and challenging formulas in our upcoming videos. Thank you for watching, and I hope you enjoy the journey. Stay with us and get ready for the next challenging proof. See you in the next video.